Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published on July 7th, 2025, just yesterday. This paper introduces a system that can capture scenes at an effective frame rate of 100 to 200 frames per second, using only standard low frame rate cameras. The paper is titled 4DSloMo, 4D Reconstruction for High-Speed Scene with Asynchronous Capture, and as we'll see, the results are really impressive. The authors use staggered cameras to achieve this high-speed capture, and then a novel video diffusion model to fix any visual errors. Alright, so this first figure really visualizes the core idea. It compares two capture methods. With standard synchronous capture, both cameras record at the exact same time. But with the new asynchronous capture scheme, the cameras are staggered, which effectively doubles the moments captured in time without any new hardware. Building on that, the right side shows the full pipeline. It starts with a baseline reconstruction from a technique called 4D Gaussian splatting, which creates 3D models that evolve over time. That initial result is blurry. The asynchronous capture improves it, but the final, crisp result comes from adding their artifact fix video model. This figure lays out the whole process in detail. On the left, we see that asynchronous capture again. Notice how cam 1, 2, and 3 are offset in time. These captured moments are then used to build that initial 4D Gaussian splatting model. But because each moment has fewer camera views, the rendered video is noisy. That's where the artifact fix model on the right comes in. It uses a video diffusion model, which is a powerful AI that refines video frames while keeping them consistent to create an enhanced video. This clean video then supervises the original model, improving it further. So this next figure shows us the architecture of that artifact fix model in more detail. It uses a powerful, pre-trained video model, but cleverly freezes most of it. The only trainable parts are small modules, added using a technique called low-rank adaptation, or LoRa, which is a way to efficiently fine-tune huge models by only adjusting a few new parameters. The model takes the noisy video and uses another model, called CLIP, or Contrastive Language Image Pre-training, to understand the first frame. Then its core diffusion transformer cleans up the video, resulting in a consistent, high-quality output. Okay, so now let's see how well it all works. This figure provides a stark visual comparison. On the far left is the ground truth, which is the perfect target image they're trying to reconstruct. You can see the other methods are either a complete blur or have significant artifacts and distortion, especially around the fast-moving hands. But their result is remarkably clean and sharp, looking very close to the original. This visual clarity supports the strong quantitative scores the paper reports, using metrics like peak signal-to-noise ratio, or PSNR, which measures image quality, where higher is better. Moving to the numbers, this table gives us a quantitative comparison on the DNA rendering dataset. We see their method, labeled Rs, stacked against other techniques like K-planes and GS4D. It's evaluated on 3 metrics. Besides the peak signal-to-noise ratio we mentioned, there's SSIM, which measures structural similarity, and LPIPS, a perceptual metric where lower scores mean the images look more similar to a person. For the first 2 metrics, higher is better, but for LPIPS, lower is better, and their method wins decisively across the board. This next table then breaks down why their method is so effective. It's an ablation study, which is a test where they turn parts of their system on and off to see what each one contributes. You can see that just switching from synchronous to asynchronous capture provides a massive improvement in performance. But then, adding their artifact fix model on top of that asynchronous data pushes the quality even further, achieving the best scores across the board. It really shows that both the clever capture scheme and the smart video model are needed for these top-tier results. So, to wrap things up, what we've seen is a really clever joint hardware and software solution for a tough problem. The key insight is that you don't need expensive, high-speed cameras. Instead, by using an asynchronous capture scheme, simply staggering the start times of normal cameras, you can achieve a much higher effective frame rate. Then, a powerful video diffusion model cleans up the resulting artifacts, creating a clean, consistent video. This combination is what pushes the quality so far beyond previous methods, opening up new possibilities for high-fidelity 4D reconstruction. That's all the time we have for today. Thanks for tuning in to the AI Research Roundup.